the organization, all the hard work that's gone into this. I've been to Daejeon and KAIST so many times, and I'm very sad that I'm not there today. So, but I look forward to seeing you all soon in the future. So I'm going to tell you about something that it's a very strong area of research at KAIST. That's, of course, your use of block copolymers for self-assembling nanoscale materials and nanoscale patterns for a variety of device applications. And I'm also going to talk about this because it centers on two papers in ACS Nano, which, and we already had the discussion about it this morning in the panel. And so I thought I would kind of do two things at once. So again, thank you very much for the invitation. So I want to just introduce the 5 people who have been working on this project. And so one is Chong Jin. So he graduated with his PhD in 2017, and he's now a staff scientist at a local startup in Edmonton. The second person is Eric Luber. So he's an engineering physicist, but he also does acrobatics, Cirque du Soleil. So it's always, don't fall, keep your head, you can break a leg or something, but just keep your head intact. The third is Brian Olson. And so here he is with one of his biological experiments. He has 2 more, and he's our coder, statistician, and analyst extraordinaire. You see his hand throughout this work. Gaia Shani Ginigay, so she's a graduate student. She's just preparing her PhD right now to graduate in January, and she's a very energetic graduate student athlete. And lastly is someone who graduated from KAIST. It's Young Dong Song. He was in Jaffer Yavuz's group, and he's now at Max Planck in Germany now. So we had a wonderful time with him and are very grateful that he spent some time with us in Alberta in the mountains. So where we got started was this idea of lithography being enabled by polymer self-assembly.
Jillian, I'm really sorry to interrupt, but looks like a part of your screen on the right side is cut.
Oh, that's terrible.
Oh, yeah, maybe you could.
Again.
Yeah. Can you try to share your screen again?
You betcha. I'm going to try right now.
Yep.
Okay. Thanks for interrupting. Is that working?
Looks like it's still there. Maybe you should close other apps that are open other than your PowerPoint. Is it PowerPoint or? Yep. Oh, yeah. PowerPoint.
This is Keynote, and so it's normally works, but let me try. If it doesn't work as a presentation, maybe I can just.
Yeah, enlarge your screen without. Yeah, even this may work.
Gosh, never had a problem before. So how much can you see?
Looks like I see the full screen right now.
One more thing.
Yep.
I'm going to do one more thing, and that is, I'm not going to optimize. Did that do anything different?
No, well, this may work because I see like options from the program, but we could still see the full screen, the full slide. I mean, a little smaller than optimal, but it looks good to me. So
okay, but this doesn't work, does it?
Oh, now it's working. I don't know what happened. Perfect.
I think you did something magic. Perfect.
Yeah, remotely. I did magic remotely. Okay, thank you.
Kamsahamnida. Thank you very much.
천만에요.
So where we got started was in this idea of using block copolymers and molecules to do the hard work of self-assembly. And so this wasn't our idea. This is something that has come out of the semiconductor industry and something you can see in what used to be called the International Technology Roadmap for Semiconductors. It's now called the IRDS Roadmap. And within that is a section called directed self-assembly. And the term that's used by the IRDS and by the ITRS is that using block copolymers to enable the self-assembly is an innovative technology. Now, the word innovative, of course, is kind of watered down and overused. But what the ITRS meant when they use that is that they're saying, hey, you academics, we think this is actually a pretty interesting way of enabling self-assembly and nanopatterning in a very inexpensive manner, but there's a lot of work to be done, so could you please do it? So that's where we had gotten started. Oh my goodness, you know, you're old when 15 years ago. And so the idea, which I know because KAIST is a real powerhouse in this area, I know you know this very well. The idea is using soft noodles basically that will self-assemble spontaneously under the right conditions. So if you have one block copolymer with a chemical composition A that's holding hands covalently with another polymer, chemical composition B here, and depending on the ratio of the sizes of these two blocks with each other and the chemical conditions, is that you can then access a broad range of different self-assembled morphologies, all the ways from this, for instance, this body-centered cube to this hexagonal cylinders to these intricate gyroidal structures, these lamellar type phases, and then the inverse. And so we're really inorganic materials chemists. And so when we looked at this, we said, oh, these are really cool, these phase diagrams that all the macromolecular people had done before us. They've done all the hard work. And so we could say, I would like a lamellar phase, the middle one here. And so you can go look on the phase diagram and find the correct A to B ratio. You can look this up and say, I'm going to make this. And if you get everything right, you will access that phase. So pretty interesting. And then when you take these block copolymers, so I get these noodles, when you take these block copolymers, depending on the chemical composition, depending what you do with them, and you confine them into a single layer, then you can use this as a template for lithography. And so the block copolymers that we work with, a lot of them have this chemical composition that you're going to see throughout this talk. This one has one block, which is PDMS, polydimethylsiloxane. And the other block here is just polystyrene. And so that's just abbreviated as PSB, B meaning block, PDMS. So just a very simple one. And so I won't bore you with the details. I know many of you, again, this is just your bread and butter, is that we're interested in the degree of polymerization, how big the two blocks are, the volume fraction, and how different chemically these two blocks are. Something called the Flory-Huggins interaction parameter, represented by the Greek letter chi. And so again, you get all the conditions right, and these molecules, these polymers, will self-assemble spontaneously under the right conditions. And so where this has seen the most attention in the semiconductor industry is for hard drives, bit pattern media. And so that's why IBM and Seagate and others have been real leaders in this field. And so the idea, again, is using block copolymers that can then encapsulate single magnetic domains that could then be used as an easy way to literally almost slosh on a block copolymer onto a substrate, and that could then be used as hard drive media. So that's where the molecules, again, are doing the hard work for you to pattern and space out these magnetic bits. Okay, so when we first got into this, there wasn't really that much work in transforming these polymers, which of course are plastics, into functional materials. And so we first came up with a way of being able to transform a particular block of polymer, this is polystyrene polyvinyl pyridine, into metallic structures. And so you could convert them into metal wires, depending on which block of polymer morphology you were interested in. Okay, we're making a single layer on a surface. These are platinum, but you can turn them into iron, into cobalt, into gold, into silver, basically whatever transition metal that you wanted. And so when you look at these, you say, okay, that's fine. You know, I can see these have a center to center spacing of 36 nanometers, but you don't have any long range order. And so I'll get into that in just a second. But the chemistry that we came up to convert these block copolymers into more functional materials is this. And so in this case, if we made a monolayer just through self-assembly of a polystyrene poly-2-vinyl pyridine block copolymer, and you put that on a surface, you can see that the polyvinyl pyridine block is encapsulated in polystyrene. It's kind of like the wire of an electrical cord. So what's interesting and what's useful is encapsulated by polystyrene to kind of keep it inert and separated. So where they go, okay, we would like to use the polyvinyl pyridine as the chemical handle through which we could functionalize the block copolymer, but it's encapsulated in polystyrene. But luckily, I had a mechanical engineering graduate student, Jinan Chai, who was working on this, and he had no fear of this. He's like, I'll get it to work. And so what we found is that when you dip this into an acid solution, is that the acid will find its way through defects in the polystyrene and will protonate the polyvinyl pyridine. It's simply a base. So the polyvinyl pyridine, which is encapsulated there in these layers, this thin layer, becomes protonated and undergoes a massive volume expansion. And so at that point, it's accessible to us because there it is on the surface. And we can then just simply then dip this into a new solution, one which contains an anionic metal salt. So it could be, for instance, PtCl4 2- or AuCl4-, whatever you metal wire you would like, just choose the anionic metal equivalent of that. You load it up, then you do a plasma step, and you end up with a high fidelity nano pattern that has the same center to center spacing and pattern as the parent blocopolymer. So you can easily convert this all through wet chemistry, with the exception of just the benchtop plasma unit, into metal nanowires. And so then you can make all sorts of interesting and fun patterns. So in the top left, for instance, you can see we're forming wires. These are all platinum in this case. These are formed inside of trenches on a piece of silicon that we actually etched in using e-beam lithography and a simple anisotropic etch, about 30 nanometers deep. The blocopolymer goes into these trenches, and when it undergoes self-assembly, it adopts the lowest energy configuration, which is one which has long-range alignment down this trench. You have a triangle in the top right. The bottom left, you have these concentric ring arrays where the dog is catching its tail. And in the bottom right, you have a defect from the e-beam lithography process where you actually have a yin-yang in the middle. And so these are actually two separate wires of platinum that never touch. And that defect is actually reproducible. So I'm going to go now to the blocopolymer that I had mentioned earlier. So this is the polystyrene polydimethylsiloxane. And so this one is forming, in this case, a very large two-dimensional crystal on a piece of silicon. And so you can see this is giving me hexagonal dots. Now the silicon that is then, which is part, of course, the silica dots, comes from the BMS block itself. So when we do spontaneous self-assembly, forming that monolayer, in this case forming hexagonal dots, we then do that simple plasma step that I had described, and the PDMS block is spontaneously transformed into the SiOX, the silica block, and forms these dots. And here's the fast Fourier transform. So this is a 3-micron scale bar. And so this is a particularly large two-dimensional grain, and so or crystal. But what we're not showing you is what you should always ask when you see this work, and you hope that authors put this in supplementary materials, is that you want to get a sense of how big these grains are, or these crystals, and what they do at the interfaces of where they meet. Because over a very large surface, you have separate regions of nucleation, and they're not contacting each other. They don't know which direction. One over here is in which it's nucleating, the other one which it's nucleating. So what happens is that they grow and tend to meet and then form a very defective interface. So this is a very large crystal grain for blockopolymers. Usually 3 microns is kind of the limit, but this one is about 10. Okay, so looks kind of interesting, hard drives and bit pattern media. And so the idea is okay, if the blockopolymers are doing all the hard work for you, you're kind of, this is an easy problem to solve. If I want to increase the density, add more, have greater number of bits or particles per square area, I'm just going to make the blocopolymer smaller. Easy. But that's not what happens. So in this case, choosing the same blocopolymer. So again, this is work from Seagate. So polystyrene PDMS. So I put the molecular weight of the 2 blocks here in red. It has a center to center spacing, often represented in the field by L. So the center to center spacing is 24 nanometers. Looks pretty good. Nice hexagonal patterning. When you choose the same blocopolymer but smaller molecular weight, the center to center spacing is 12 nanometers, represented by L. But you can see the one on the right just looks awful. Okay, so that's because something called your segregation force is diminishing. And so if you take this to the extreme where the polymers get smaller, at some point they just simply isotropically mix. And so you don't get any nanoscale phase segregation at that extreme. So you can see you're approaching that extreme. So simply decreasing the size of the blockopolymers doesn't work. Now you have interesting people, Grant Wilson, who's an editor at ACS Nano, Mark Hillmeyer, editor-in-chief of macromolecules, for instance, people making very high chi parameter type locopolymers. But what we are wondering if we could do is if we could hack this. And so the way we hack this was by creating, in this case for cylindrical arrays, we would double that single layer to form a density doubled layer. And so when we then go and take these cylinders of, let's say they're polystyrene poly-2-vinyl pyridine, we metallize them and treat them with air plasma. So normally the block of polymer gives you its native spacing of L, but you can see that in the double layer in the top image there, that these are a bit like putting two cylinders on their side, like paper towels or toilet paper. If you put them on their side, the lowest energy configuration, if you put another layer on, is at that interstitial space where they meet. And so when we metallize this, treat it with that simple air plasma, we're reducing the dimensionality from 2 to 1. And so that top layer falls between the two. And so you get you decrease the spacing between these two by a factor of 2. So the periodicity or the spacing, L, goes from L to L over 2. And you haven't even changed the block of polymer. So you can choose a block of polymer that gives you nice regular patterns because it's sufficiently large, has good segregation force, but then we decrease it by a factor of 2. And so this actually works. And so we're looking at the single dots and the single lines, and then we can make the doubled lines from the top to the bottom. Now, there's one little caveat is that you can see that the single lines, so these are all 100 nanometer scale bars, is that the fidelity is not perfect. And so the single lines are all bright, but when we double it, you can see that it kind of goes bright, dim, bright, dim. You see this alternating pattern. It's like, what's that due to? And I'll explain that in a second. It seems to also work with dots. And when you look at the tilted SEM in the top right-hand corner, you can again see that bright, dim pattern that we see. And what that's due to, you can see in AFM, the AFM imaging that we did in this paper is that this is simply the bright, dim is an artifact of the electron microscopy imaging. So the bright ones are very tall, and those ones are derived from the top layer. And then the ones at the bottom are flat, and those are the ones derived from the bottom layer. And so it's just good. It's tall, wider, and flat. Taller, wider, and flatter. So it's not perfect. It's not a perfect way to hack it and to decrease the spacing. It's also compatible with Graphoepitaxy. Graphoepitaxy is a horribly fancy word for just saying, I drew some lines, like I took a flat field and I put in curbs so the cars know where to drive. So they have directionality. And in this case, we drew lines of silica on a surface. And when we carry out the block of polymer self-assembly, again, you see that motif of bright, dim, bright, dim, bright, dim that is derived from where the cylinders arose from, whether they're on the top or on the bottom. You can also see it as part of a large circle that we drew. Again, that bright, dim, bright, dim. So yes, you can decrease the spacing by a factor of 2. You can hack it, but it's not perfect. And so Shin, so he's the heavy weightlifter guy, he said, all right, what if we can do density tripling, but I'm going to separate these 3 steps and increase the complexity of the processing, admittedly. Okay, so this is just fundamental science. But he did a spin casting and annealing of a block of polymer, polystyrene block PDMS, that gives you the dots. Plasma etches it, gives you the dots. So there we just have silica dots. And then he spin coated another layer of the same block of polymer. And so at this point, we had no idea whether the second block of polymer self-assembly process would register with the first one or whether we would get a mess. If it registered, you get a honeycomb pattern. And then if you then spin coat yet another layer on top of these now silica dots, would you get the triple density film? And so that, in fact, you do. So initially up in the top in A, you can see these are the blue dots that represents the single layer. And then you can look at the corresponding scanning electron microscopy micrographs. And then you can see when you put on the second layer represented in green, you actually do get registration. At the time, we had no idea, but they do register. So the particles or the dots underneath are large enough to force the block of polymer above it as it's self-assembling into a lower energy configuration that has this registration. And then when we put in the third layer, the yellow, you get a triple density pattern. Okay, now it's the human eye is very good at recognizing patterns, and it lights up our pleasure sites in your brain. That's patterns are kind of what enabled humans to survive over the millennia. So you want something a little better than that. And so what we did was to write some software. This is Brian, the one with the 3 kids, write software that would actually analyze and quantify quality. Because again, you look at these things and say, oh, aren't they pretty? But Brian would write an algorithm, and then we would feed these SEM images into the algorithm, and you could then see, so you could see the one here with 17 plus or minus 3% overlap. The dots that are colored in blue are in fact in contact with each other. And so if you're interested in bit pattern media, then that's telling you, oh, actually 17% of these dots are in contact with each other. But once you have this algorithm, you can then go and actually quantify quality. And this is actually something that the industry people in hard drive manufacturing had asked through the roadmap to the academics, can you please come up with better ways of being able to quantify what good is? Because it's so easy to just show a pretty picture and say, oh, isn't that nice? And in the bottom right-hand corner, you can see there's 3% overlap. And so once you have a way of being able to quantify quality in a statistically relevant way, then that gives you a rational means of improving. Now, one thing that Chong did, again, the weightlifter person, is that he said, okay, I'm going to do that first block of polymer self-assembly, form the silica dots. But the second block of polymer I'm going to put on there, it's not going to match. It's going to be different. And what's going to happen? Now, at the time, what I thought would happen, he didn't even tell me he was doing this at the time, is that the first layer would dictate to the second layer with a different spacing, a different natural native spacing. But these are soft materials. I assume that it would force the second layer to adopt the same periodicity. It would just get thicker or something like that. That's not what it does. The second block of polymer says, no, my native spacing is this. So if I'm going to lower global energy, I'm actually going to adopt a slight offset of rotation and adopt a Moiré superstructure. And so again, Brian, what he did is he would then take these SEM images, and Chong, by the way, came to me and said, I see triangles everywhere. Brian wrote an algorithm that would take these SEM images and automatically separate the top layer from the bottom layer. And just to show you that this is real data, underneath this 250 nanometer scale bar, you can see 3 fat dots and three small dots, and you can see them in the corresponding separated red and blue images. You can put them back together, but once they're separated, what this allows you to do is to determine the angle of offset of these two lattices. And so what this showed is that in order to adopt the lowest energy configuration that the system could under these conditions was to take on an angle of rotation of 3 degrees. And that's then giving you these Moiré superstructures. So at the time, we had no idea what was driving this, or we had no predictive power at all as to being able to predict where these things were going to go. And so what Chong did, that he then took 3 combinations of local polymers. He took a small plus a medium, he took a medium plus a small, and then took a large plus a medium, and we simply put them together using Brian. And then you see these either triangles or what we call flower patterns. Brian would then use his algorithm to separate the bottom layer from the top layer, which then allows you to determine that angle of offset. And so in the combination on the top, the angle of offset is 30 degrees. The one in the middle is 11 degrees, and the bottom one is 3 degrees. But we had no predictive power, and we had no idea whether this was even interesting to anybody. So here's just a very large grain. This is one of the 11 degree images or offsets. Okay, taken with a helium ion microscope, so you can get a very large field of view. Now, I did not tell you the whole story, and that is that we actually have defects because you have nucleation sites at different places that are not in communication with each other that grow from those nucleation sites. And so I'm hoping that this video comes out. This is a very large helium ion microscopy image. So again, the center to center spacing of these dots is about 30 nanometers. And this is a 30 micron by 30 micron image. And what Brian did is that he then wrote an algorithm that would actually color code this by the angle of rotation. And so what you see is that red is plus or minus 30 degrees. So these are in fact chiral phases. And then in the middle, you can see that he adopts the more neutral blue and green. And so what this allows you to do is to take a very large image And then again, to be able to statistically analyze and to be able to look to see whether are you simply getting a mess of things or are you getting a majority phase? Does the system find the lowest energy configuration? And as you zoom out of this kind of Google Earth type viewing of this 30 micron by 30 micron image, is that you can actually see that the majority of the phase is, you see a lot of this red. And so that's telling us this is a majority phase. And the purpley flower phases of the defect sites are actually forming where you have a lot of defects where grains are meeting underneath. And so the system's so frustrated, it doesn't know what to do. But once we have a statistic way to be able to do the stats on these things, we can actually determine whether or not these are majority phases. Okay, now, I didn't convince you at all that you're getting anything other than a mess. And I don't think Chongjin was convinced either. So what we wanted to do, because we do a lot of machine learning type with sparse data using experimental results, was we wanted to generate statistically relevant data to have any sort of sense of being able to do prediction. And so what he did was to actually use electron beam lithography to draw in the first silica dot pattern, the hexagonal dots. Instead of using the block of polymer to do it, we used e-beam, because then you can go and on a single chip, you can go and make the spacing 10 nanometers, 12 nanometers, 14 nanometers, all the way up to, to 80 nanometers, all on a single chip. And then you can do the block of polymer self-assembly on that chip. And so you're doing it all under the same conditions. You can then go and etch that and then go and analyze these. And so he did 2,800 templates in order to be able to generate some data from which we could actually do some sort of machine learning type analysis. So these are just some of the circular posts that he made by e-beam lithography, 5 micron scale bar, so you can't resolve the individual dots, but here's one. So again, we're not using the block of polymer to do the first one, we're using e-beam, so we can have precise control over the spacing. And when you put a block of polymer, polystyrene PDMS on there, again, you see Moiré superstructures all over the place. Okay, so what this allowed us is when you have 2,800 combinations, is that we saw Moiré superstructures everywhere. And I'm not going to go into detail. This is a subset of 35, but just to give you a sense that so this is why we needed Brian to then be able to analyze these, produce the algorithm that would allow us to analyze these and to be able to pull out data. Now, one thing, Brian, he came to us and he said, this is really weird. I'm seeing these swirly patterns everywhere. So we were seeing these triangles, which just look like standard Moiré superstructures. But he was seeing these swirly patterns and they were chiral. So we'd see here, just because this is the color of this legend on the y-axis here on the far right, you can see the green ones in one direction and the pink ones in the other direction. And by the way, this is an achiral surface. So you see a 50-50 ratio of both, which is what you would expect. But he saw these rotations everywhere. And he's like, wow, doesn't this kind of remind you of, a Van Gogh painting? So what this led us into is that these are in fact static distortion waves, and or mass distortion waves, depending on which physics class or who taught you physics when you were an undergrad, is that what's happening is that in addition to the Moiré superstructures being formed, in which the two lattices adopt an offset in order to reduce the global energy of the system, it undergoes a final little twist in the core, which also adds to lowering the global energy. And so we thought, oh, isn't that kind of cool? But who cares? I mean, who would care? And then Eric, so he's the Cirque du Soleil guy, went to an American Physical Society meeting in 2019 before the global pandemic, and his talk was absolutely packed. People said, we really need this as a model for understanding what's going on in some of our two-dimensional structures. And so these static distortion waves actually go back to, they were predicted in 1977 in a Physical Reviews Letters paper. And we're actually in contact with Anthony Navacco, which is really, really cool. So he's a professor emeritus, but he had predicted these. And he had predicted them, he and McTagg had predicted them on graphene surfaces. So people say, well, graphene, that's so new, but we're talking PG here. And that if you have a crystal of, say, xenon or some other inert gas, is that if they don't match, is that the system will adopt an angle of offset, just like what we're seeing, Moiré superstructures, but can actually adopt that little twist, that static distortion wave, in order to further lower the global energy. And this has suddenly become so interesting because you're seeing this all the time in these magic angle two-dimensional sheet structures, twisted bilayer graphene, just leading to crazy properties, ferromagnetism, these correlated insulator behaviors, superconductivity, things like this. So interesting. And so these static distortion waves are also seen in these twisted structures. And so here, just another example. So we were just seeing them absolutely everywhere. So this was a ubiquitous example of this, of how the system is trying to lower energy. And so we wanted to go from dots to maps. And so again, I had asked Brian one day, are these grouped together? These little chiral twists? And it turns out they kind of are. Now, we didn't have a lot of insights. This is the very last thing I'm going to show. It's a molecular dynamics simulation that uses LAMP's open source software from Sandia. And so what Brian did is that we are underneath here. I'm going to then go and I'm going to heat this, okay, to give you a homogeneous melt. But underneath we have a hard hexagonal post system that's been modeled. And we're going to put a soft, mushy polymer over top, and we're going to see what happens. Okay, so in this model, we've melted the epi layer. Okay, so it's a homogeneous melt using a nose Hoover thermostat. So when we give the system time, and we give the system energy, so thermal energy, is that you start to see some of these triangular patterns that are typical of a Moiré superstructure. And we're going to speed this up because otherwise it's like watching paint dry. You can see the circle in the background that represents those hard dots. Again, we're going to speed this up, and you start to see those twists, those static distortion waves appearing. And so these are nodes of structural relaxation. So here we are, we've given the system energy. And you can see how they're actually grouped, kind of exactly what we saw experimentally. Down in the bottom right-hand corner is a histogram, and this histogram is telling us the angle of offset. So this is a plus or minus 11 degree rotation. We're cooling the system down, and it's giving us a motif that is very similar to what we saw experimentally. And so once you have a model, then you can actually use that to try to pull out what's going on with respect to the interaction with the soft material to the soft material, the soft material to the hard material underneath, to understand the origin of these static distortion waves. So just to summarize, I hope I've shown you through some papers in ACS Nano that polymer noodles, and again, I know you know this at KAIST because you're a powerhouse of this area, that they can be used to access a wide variety of patterns, and that you can also hack the equilibrium structures. You're not necessarily limited by what the polymers will give you, and that you can actually expand the repertoire of patterns. And that they actually can be very surprising, far more than simple hexagonal or linear structures, static distortion waves. So again, I just want to acknowledge the people who did this work, and thank you for the chance to speak today, and I'll be happy to answer any questions.
Oh, thank you very much. Your wonderful talk. And I'm also very impressed by athletic skills of your former students. And so I have a question from student. So let me lead it for you. I have a very rudimentary question regarding the static distortion waves. How could a two-layer pattern, where the same patterns are just be twisted with respect to each other, have different contents of distortion with different chiralities? Is it because each pattern does not have uniform distances between each particle?
Okay, so so just experimentally, the static distortion waves were actually not seen until 2016 in an ACS Nano paper, actually, by Fritz and coworkers in Germany. And so maybe if I just describe that really fast. So they have an HOPG surface, so that's basically graphene surface. And they were looking at these coronine molecules that would spontaneously self-assemble to form a lattice array, a two-dimensional array on the surface. And they were analyzing this by scanning tunneling microscopy. And they noticed very small deviations in the actual bond lengths of the carbon-carbon bonds in these coronine molecules, because the lattice const of that one-dimensional layer of those crystals did not match that of, sorry, it's a two-dimensional layer, did not match that of the underlying graphene. And so the system would undergo a small distortion in order to lower energy. It was actually stretching bonds. So if you look at that Fritz and co-workers paper from 2016 in ACS Nano, you put in static distortion waves. It's actually in the title. That is a great start. And so really these are, even though they're chiral, the molecules, the bonds, they don't know what chirality is. And so it's simply the system just undergoing an extra little twist, if that is energetically favorable, to lower the energy of the system. And of course, you're going to get a 50-50 mixture of both directions. It's just like a whirlpool is itself chiral. And so you're going to get regions of one chirality and regions of another chirality. So it's chiral sounds like, oh, it must be biological, but no, it's just simple stretching of bonds, or in this case, the block of polymer spacing. I hope I've answered your question.
I'm sure it does. So thanks for your answer. And second question is, are the static distortion swirls able to be reversed, for example, by thermal annealing?
Oh, that is such a good question. So when you thermal anneal these, so this gets into the whole business of block of polymer self-assembly for the semiconductor industry and annealing out defects. So in essence, are these defects, is it a bug or is it a feature? So what would happen if you heated this up is that you're actually going to melt it, and then it will simply it will form something a completely different pattern of static distortion waves that won't have any memory of where they were before. So could you do a selective heating where you heat them up just enough that they could, that's an excellent question. I bet you could. So just enough heating that the system has a bit of mobility, and you could change them without removing all of the self-assembled structure that you actually form. It would take very careful experiments, but possible.
Yeah. Maybe you could answer that in your next talk here at KAIST. Okay, so let's thanks Jillian again.
Thank you so much. 감사합니다.
예, 천만에요.